Well, thanks for hanging around. And my name's Kip Carrico. I'm faculty in civil and environmental engineering. I'm not going to take too much of your time. In fact, I didn't even put a title slide because I want to save your time. But anyway, we're going to talk about air quality and the atmosphere. We talked about water last session. And unlike water, we have no problem with the quantity of air, right? We do have problems with the quality, and this is just a IPCC chart showing the rated forcing. So you can think of it, it's a tweak in the energy balance for the atmosphere and for various different forcing agents. And the usual culprits, CO2, methane, but on down the list. But also significant are aerosols. That's something we study. There we go. SO2, organic carbon, black carbon. And as you can see, there's a big uncertainty bar on those. And so that's really what is driving a lot of our research. Health effects as well, but basically the net cooling impact due to aerosol particles. And so if you add it all up, the net total is about these positive ones are warming impacts and these negative ones are cooling impacts, about 3 watts per square meter. And I make my students do this. They have to calculate, well, what does that mean? What's a few watts per square meter? You guys know that climate change is important, but just to emphasize to them, what's this scale mean? And they have to see, okay, well, how many full scale nuclear exchanges does that amount to? And it's about 1 full US Russia nuclear exchange about every 5 hours in terms of the joules being added to the system. So it's a lot of joules going into the system. It's like 5 Hiroshima blasts every second. So, and then they can make their determination: is that important? Is it not? Something we need to focus on. But these kind of list out the species that we need to monitor. Do we need to do a lot of further study in terms of CO2 and its impacts on the atmosphere? 19th century physics, we know how that works. Okay, there's different isotopes, but a molecule of CO2 is a molecule of CO2, whereas aerosol particles, their size, their shape, their chemical composition, that all contribute to these big uncertainty bars for those contributions. So, and that's what we're interested in measuring and monitoring how that changes over time, because it has changed, right? We've had a Clean Air Act that was remarkably successful, right? We've cleaned up our atmosphere over the last 50 years substantially with respect to those species, but not with respect to greenhouse gases, right? So, and you can see that in terms of some of the changes in that we've noticed in our emissions over, the past couple decades. This is comparing 1990 to about 20 years later, 2000, about 20-year time frame changes in emissions. And we've seen these circles in terms of major CO2 sources shrinking, right? Some of them going away, right? We know that we're in New Mexico, we've been taking a few large coal-fired power plants offline in this area. And, these are some of these big sources here. And like the rest of the world, or at least the industrialized world, those sources are getting retired, right? And, the last coal-fired power plant in the UK just shut down within the last week or two. And we know that the things are changing, and that's San Juan there. So, but that's not happening everywhere in the world, right? There are still coal-fired power plants being built in other countries. But when we want to look at monitoring of the atmosphere and important atmospheric species, and you can really look at it from the top of the atmosphere to the bottom. So, satellites. We now have a wide variety of satellite tools for measuring trace gases, even for measuring these tricky aerosol particles. And so that's becoming much more common, much better constrained in terms of what those are showing. Just as an example, that's between that and aircraft measurements, that's how we discovered, the methane hotspot over the Four Corners area. Those kind of measurements are able to detect those large scale events, right? So, a little bit further down below, maybe where the aircraft are doing, we can do eddy covariance and look at fluxes, right? And some of the recent measurements related to, we can look at fluxes that are getting absorbed by natural, biogenic sinks, right? And we can also look at sources of CO2 or aerosols that are being emitted. Say, for example, if there's a leaking reservoir in which we're putting CO2. And so these are monitoring techniques to watch for those sort of events. And so, and then, going a little further down, you've got all sorts of imaging techniques to find leaks in our energy infrastructure and things of that nature. You can then even monitor soil emissions, and then further down go into the subsurface, right? And monitor with groundwater wells, look for, some of the same issues do we have. If we're putting CO2 underground, is it staying where we want it to stay? So just in terms of what we do, this is just one example, one taste of that. We're measuring emissions oftentimes from wildfire emissions, right? It's been we've seen a lot of changes, right, in the last 10 to 20 years in terms of wildfire occurrence, their severity. And so we go, for example, to this Konza Prairie in Kansas, and we're doing drone-based measurements of wildfire emissions and looking at how those change, right? Things don't stay the same in the atmosphere when you're talking about aerosols. They evolve over time. And so, with some of these small new sensor techniques that are drone mountable, for example, or, can be used in other applications, you can see, these, really interesting changes in aerosol properties where, we go from a darker aerosol that's more black carbon dominated, which you can see, low wavelength dependence, to high wavelength dependence, which is more brown carbon as the fire falls apart into a more smoldering stage. So, and, I guess that would be my take-home message. We've got a lot of changes both in the natural environment that, we're seeing in our neck of the woods. It's, what's happening with wildfire events, what's happening with dust events, and how those are, threatening to roll back some of the changes, the improvements in air quality that we've had over the last 50 years, right? The Clean Air Act has reduced SO2 emissions 90%, something like on that order. But we're seeing a lot of places where we're starting to backtrack in terms of air quality. We're starting to see worse air quality in places, Pacific Northwest, for example, where we have these, year after year, these wildfires that are becoming more intense. So, and there's, Ruidoso, plume from that, right? These are satellite scale events. And so, and, we don't want to exacerbate these with poor choices in terms of our, as we evolve our energy system, and, whether it's, solar farms disturbing the soil and creating more dust, or carbon capture and sequestration, all of these, we're changing the surface of the earth. And so we want to do that in the most sensitive way we can. And I'll just leave that at that.